Non-terrestrial networks represents an exciting new direction for 5G mobile communications, with some interesting challenges and opportunities. I'm Rob Maunder, CTO of AccelerComm, and I'm here to introduce LEOphy, which is our solution for the physical layer of 5G NTN. AccelerComm is an IP company. We write system Verilog code that runs in FPGAs and ASICs, as well as C code that runs in embedded x86 and ARM processors. And we license this code to our customers who put it into their chips and put it into their boxes to build 5G equipment. We also support our customers with reference solutions which have all of the IP running together on a board. The demonstration we have for you here is showing the LEOphy being asked by layer 2 to transmit the SSB. This is the synchronization signal block. We will show that it's being successfully transmitted and captured on test equipment. The SSB is a broadcast signal transmitted by a base station, so in this case a satellite, to advertise its existence and allow user equipment on the ground to connect and to synchronize with that base station. The demo comprises 3 different components. We have layer 2 and above running on an x86 machine, and this is connected to the LEOphy board by an Ethernet cable. The Ethernet board is transmitting via SMA connectors into test equipment of a vector signal analyzer where we can see the signal being successfully received and synchronized. The process that we're observing here is of the layer 2 and the LEOphy connecting together and negotiating their engagement through P5 messages from the NFAPI protocol. This connects them together and enables them to work together. Then we have the layer 2 issuing a P7 downlink TTI request, which concludes a master information block, which is being provided by Ethernet cable to the LEOphy. We have Wireshark inspecting all the traffic that flows backwards and forwards between the layer 2 and the LEOphy layer 1, and it allows us to inspect the P5 messages and the P7 messages so that we can see that the command is being correctly issued. On the LEOphy board, we have a polar encoder running in hardware acceleration, which is encoding the MIB using the PBCH encoding channel. Also, the LEOphy is appending DMRS reference signals, as well as the PSS and the SSS synchronization signals, which get combined together to produce the SSB. The LEOphy is then putting that through the LOPHY, running again in hardware acceleration, and transmitting it through the SMA connectors to the VSA. The VSA is then successfully receiving it, and on the scope here we can see the 5 MHz signal being successfully received. We have constellation diagrams illustrating the QPSK and BPSK components of the various different parts to the SSB, which I described. And also we can see, crucially, that the signal is being synchronized. In summary, we have successfully demonstrated the LEOphy transmitting the SSB. This is an end-to-end demonstration starting from layer 2, coming through the NFAPI interface, through the physical layer, and out to test equipment. There are a number of advantages to this solution. It's performant. The hardware accelerators are optimized to deliver high throughput, low latency, power efficiency, and also optimized wireless performance. The solution is portable. It can be adapted to run on a variety of different FPGA boards from different FPGA vendors, as well as ASIC. And it's a complete solution encompassing the entirety of the 5G physical layer as a marriage of optimized hardware and software which has been jointly designed. It's standards compliant. It uses all of the latest 3GPP standards for 5G NTN, as well as the small cell forum standard for NFAPI and the ORAN front haul interface as well. It's flexible and can be deployed across a variety of different use cases, not only in NTN, but also in terrestrial, such as small cell and macro cell as well. And it can be adapted to meet your particular requirements.